Welcome to this introductory video for Module 5A. As typical, we start with an engineering disaster to review. On July 17, 1981, two overhead walkways in the Hyatt Regency Hotel in Kansas City, Missouri collapsed, killing 114 people and injuring 216. Loaded with the partygoers, the concrete and glass platforms crashed into the lobby floor. The collapse resulted in billions of dollars of insurance claims, legal investigations, and city government reforms. Convicted of gross negligence, misconduct, and unprofessional conduct, the engineering company lost its national affiliation and all engineering licenses in 4 states, but it was acquitted of criminal charges. The hotel had been built just a few years before during a nationwide pattern of fast-tracked, large construction projects with reduced oversight and major failures. Investigators found that the collapse was the result of design changes to the walkway's steel hanger rods. The original design specified 3 pairs of rods running from the second floor walkway up to the ceiling and passing through the beams in the 4th floor walkway. The manufacturer of the rods, however, proposed that 2 separate and offset sets of rods be used, the first set suspending the 4th floor walkway from the ceiling, and the second set suspending the 2nd floor walkway from the 4th floor walkway. This design change proved to be fatal. When we consider stress failures in machine members, what type of stress actually causes the failure? Is it the compressive stress? Is it the shear stress? The tensile stress? Or some other type of stress? Obviously, this depends on several factors. We can begin to develop insight into this by considering Moore's circle. Recall that even when we have a case of just normal applied stress only, there is still a resulting shear stress. Here's the Moore circle. We have applied normal stress, and yet we still see we are getting shear stress. The shear stress is effectively 1/2 of the normal stress. It is important for us to understand how stress results in failure so we can properly design our systems to avoid failures from occurring. How a part will fail is dependent on how it is loaded. The material type is also a factor. Ductile materials are limited by their shear strengths, whereas brittle materials are limited by their tensile strengths. Remember, ductile materials will have greater than 10% elongation at break. Brittle materials will have less than 5% elongation at break. Between 5 and 10%, it's somewhat of a transitional range and may require an evaluation in both brittle and ductile failure modes. A ductile component will generally fail by yielding and is thus limited by its yield strength. A brittle component generally fails due to fracture and is thus limited by its ultimate strength. Later in the course, we will study cyclical failure, wherein a ductile component may fail by fracture and behave as if it were brittle. Fatigue failure is another name for cyclical failure. Up to this point, we have been discussing static loads. Static loads are applied slowly and remain essentially constant over time. Dynamic loads are applied and then may be removed, or they may fluctuate in their magnitude. These constitute types of cyclical loading. The chart shown here breaks loading cases into 4 different classes. 2 terms that are synonymous in methodology but different in application are design analysis and failure analysis. Design analysis is performed before the product or system is built. It is intended to prevent failure from occurring. Failure analysis is performed after the product or system has experienced a failure. This is also referred to as forensic analysis. Sometimes the terms design analysis and failure analysis may be used interchangeably. They are technically different applications, but the processes are nearly identical. When you approach either a design or failure analysis, you start by looking at the loading and determine whether it is static or dynamic. If the loading is dynamic, you have three methods to choose from: stress life, strain life, or linear elastic fracture mechanics. In this course, we will only focus on stress life. If the loading is static, then you must decide whether the material is brittle or ductile. If it is brittle, we will use the modified Moore theorem. If it is ductile, we will use the von Mises stress theorem. There are 5 common theorems for the failure of ductile materials. Several of these have been superseded by later methodologies. The von Mises theorem is the accepted method for ductile materials, while the maximum shear stress theory is basically a subset of the von Mises stress. We have covered most of the material on this slide in previous lectures. Note the 2D and 3D von Mises theorems with a version based on the principal stresses, as well as a version based on the applied stresses. Either of these options will result in the same answer. It comes down to which one is more convenient to use in a given application analysis. The factor of safety for ductile materials is based on the material yield strength divided by the applied von Mises stress. In the bottom left, we have an example of a stress envelope diagram. This is the graph of the ratio of principal stresses to yield strength for a given material. The plot here is a 2D representation of a 3D system. That's why it's elliptical. Within the area of the ellipse, the ratio of principal stress to yield strength is within safe limits. That is, the factor of safety is at least 1 or greater. Outside of the elliptical area, the factor of safety is less than 1 and therefore unsafe. The closer you get to the origin of the graph, the safer the design becomes. You can measure the distance from the boundary line here to any point of reference within the elliptical zone. That distance is effectively the factor of safety. What we're going to do next is overlay various failure theorems onto this type of envelope chart and compare and contrast the theorems to each other. First, we are going to look at cases of pure shear. When the only stress is torsional shear, then the equations shown apply. The shear strength for a given material is 0.577 times the tensile yield strength of said material. Thus, the factor of safety in a situation like this can be defined as 0.577 times the tensile yield strength divided by the torsional shear stress, or else it's also equal to the material shear strength divided by the torsional shear stress. Remember, in this situation, sigma x, sigma y, and if necessary, sigma z are all equal to 0. So if we take and apply the von Mises stress to the same situation, these terms here are all going to go to 0, and what we'll be left with is simply the von Mises stress equal to the square root of 3 times tau xy squared. Thus, we can equivocate this set of formulas. So the yield strength of the material, the tensile yield strength, divided by the von Mises stress gives you the factor of safety. It is also equivalent to the shear strength of the material divided by the applied torsional shear stress. And in homework 4.1, we have a case of pure shear, and the solution shows the factor of safety being determined by both methods with the exact same result. We're going to end the video here, and in the next video, we're going to look at and compare the different failure theorems for ductile materials.